So we're going to get to module 5. We're now looking at chemical equilibrium. I am going to go quite quickly, but just remember you can always pause the video and rewatch it if necessary. Okay, so here we go. When we look at chemical equilibrium, first we've got to define some terms. Number one, what is an irreversible reaction? Okay, well, in a normal reaction or in any reaction, the reactants are used up and the reaction will then go to completion. So these are the sort of graphs we've seen already. So we start with lots of something and then we end up with nothing. So that means it goes to completion because we've used up all the reactants, such as things like the combustion of fuel. We use up the fuel's gone, and we can't reverse it. We can't then take the products and make them back into whatever the reactants were. So the reactants become products. That's nothing new. You've seen this lots. With a reversible reaction, the reactants don't get completely used up because what happens here is that as the reactants get used up to make the products can react to form reactants again. And that is actually really, really important, okay? So so what happens is the reactants and the products are never actually completely used up. They are constantly reacting and constantly being produced. So as reactants make products, products make reactants. So we use a double arrow. There must be half arrows because they represent two halves of what's happening. The first one is reactants becoming products, which you read from left to right, and then products becoming reactants, which you read from right to left. So what does that mean for us? My reactants start with lots and they get up and you end up with less. My products start with nothing and I end up with more. Now, we don't have to end at a place where the products are more than the reactants. That's just the example. However, what's really, 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 really important, the reactants cannot go to zero. Okay? You must have reactants left. That's very important. Now, the forward reaction, because this is an important term, is the reaction that happens when the reactants become products. It's how we always read chemical reactions, okay? It's the forward reaction, going from reactants to products. The reverse reaction is when the products become reactants, okay? And that's also important. So that's the other way around. The products become reactants. So these are the two halves of what's going on in a chemical reaction. Now, what's important with the reversible reaction is that both happen simultaneously. So they happen at the same time. Once the reactants start making products, the products automatically and naturally become reactants. Okay, it has to happen all by itself. It doesn't need us to help them do that. Now, we need to talk about what an open and a closed system is. An open system continuously interacts with its environment. Okay, so that matter and energy can be exchanged. So this is where we can lose a gas into the system. Okay, and it could get hot, it could get cold, it doesn't matter. I'm not really worried about the change in the energy to the system. What we're worried about is the matter, the fact that sometimes things can be lost to the environment. Closed systems, we can have an exchange of heat, so they can get hot or cold, but not matter. So the matter in the system remains constant. Okay, so we have it all keeping together. All right, so you need to be careful with that. In order for an equilibrium, which is what we're talking about now, happens, we need to have a closed system. Nothing should be allowed to escape from that system. Okay, very, 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 very important. Now, a dynamic equilibrium means that the forward and reverse reactions continue to take place simultaneously, so together at the same rate. So we make products as quickly as the products are making reactants. We're going to use a phase equilibrium as a way to illustrate this, okay? So when we have water, so this is water in a beaker, or a test tube, let's just go with it, okay, the water evaporates. Makes sense? At any temperature, the water evaporates. In an open system, the water evaporates, it's allowed to escape, it can go into the environment around it, and very little will condense back into the container. So once it goes, it's lost. It's an open system, okay? And you also know that if you leave a glass of water somewhere, eventually the water will all disappear out of the glass, okay? How do we write this? Well, we say that H2O, it should really be a half arrow, much bigger arrow to the right. So I'm telling you, I'm getting lots of the gas. Very little of it is becoming water again inside the same system. Okay, it may condense somewhere along the line, but just not in the system. If I close the system, okay, and probably would have been better just to put a lid on there rather than put a bell jar over it. It doesn't matter. We close the system. Water evaporates at any temperature. That's what's going to happen. But it's not able to escape. So that means water is becoming a gas, but because condensation can happen within the system, it can go back into the system or into the container. So we're not losing anything. What you would see is you would see the water drop, you'd see the water level drop, and then eventually it would stay constant. And it would look like nothing else is happening. But that's simply because as quickly as it's evaporating, it's condensing. Okay, so eventually the rate at which it evaporates equals the rate at which it condenses. There's stuff happening, which is why it's known as a dynamic equilibrium. Okay, so we can reach a point where H2O, liquid, becomes gas and gas becomes liquid. And they happen at the same rate, and we're all happy with that, okay? Dynamic, because there's something always happening. Phase, because we gas to liquid, liquid to gas, okay? You don't get this with, it's harder to see with a liquid and a solid, but I guess you could get that, okay? In a chemical reaction, we can also have a dynamic equilibrium. So now we're looking at the rate of the forward reaction and the rate of the reverse reaction. So we've got to actually have a chemical reaction. So we've got things changing. Reactants become products, products become reactants. Okay? Look at the graph. Now this line, unfortunately, shouldn't really be there. It should probably be about here. This is the concentration of the reactants and the products. We start with lots of reactant, no product, and then we get to a point where these lines start to look like they're going straight. Okay, so these concentrations are becoming constant. They do not have to be equal. This is very important. The concentrations have to be constant, so it's going to look as if we're not making any more any more product, and we're not making any more reactant. So when equilibrium gets released, what we call chemical equilibrium, the substances do not need to be equal. Okay, but they must remain constant. Okay, because as quickly as we're using reactants, we're using up the products. Okay. If we look at the rate graph, it's a little easier to see. So, and with these, it's always a good idea to maybe trace them in a color. Forward reaction starts fastest because we start with the reactant, and it slows down. Why? Because we're using up the reactant, so it's going to get slower. We understand that from rates of reaction. The reverse rate is 0 and speeds up because as we're making more products, that means there's more substances available for the reaction to take place. That will speed up the reverse reaction. Eventually, the rates become equal. Okay, very, very important. So the forward reaction starts fast and then slows down. That's what I showed you at the top there. The reverse reaction starts slow and speeds up. That's shown over there. And eventually, when equilibrium is reached, the two rates are equal. This is the important thing. Okay, so that's the important thing for this first part.